In this lecture we are going to talk about dynamic programming. Dynamic programming is an algorithm design technique where the problem is broken down into simpler subproblems, and the final solution is calculated from the solutions of these subproblems. The solutions of solved subproblems are stored and when needed can be reused for future calculations. The dynamic programming technique can be successfully applied only for problems that have optimal substructure and overlapping subproblems. Dynamic programming helps to reduce the space of subproblems in the way that overlapping subproblems are solved only once. Dynamic programming offers two approaches for space reduction of overlapping subproblems. Memorization, also known as top-down approach. This is a process of storing the solutions of subproblems in the table. At each further calculation step, the algorithm checks if it has the solution stored in the table, and if so, the solution is reused instead of calculating it repeatedly. Tabulation, also known as bottom-up approach. This is the process of solving the subproblems first and directly using this solution for solving a bigger subproblem. This approach usually operates in an iterative manner. Let's take a certain problem and try to solve it. We need to implement a function which returns nth number of Fibonacci sequence. Fibonacci sequence is a sequence of integer numbers such that each number is the sum of two preceding ones starting from 0 and 1. The most obvious naive solution looks like this. We have a recursive function Fibonacci number. We have two base cases for n equal to 0 and n equal to 1 or 2. At these points, function returns either 0 or 1. At the recursive step, we calculate sum of two preceding numbers. Here we have two recursive function calls. Now we are going to analyze the time complexity of this function. Let's say we want to compute what is the sixth Fibonacci number. So we add number 6 to our recursive function call. Since it is a recursive function, we cannot get the result until we reach the base case of our function, which is reachable only when number is equal to 2 or 1. So we dive deeper into the recursive calls and call the function with number being equal to 5. Again, we need to go to the next recursive call where number is being equal to 4. Similarly, we reach 3 and 2. Remember that when number is equal to 2, we reach our base case and can return the result, which at this point is equal to 1. Since we have two recursive calls in one function, we need to make another recursive call. This time the parameter number is equal to n minus 2, and at this point it is equal to 1. 1 is our base case, which returns the result being equal to 1. Now we can calculate the result of a function call where parameter number is equal to 3 and the result here is equal to 2. Now we need to make another recursive call with parameter being equal to 2. It is also a base case, therefore the result is equal to 1. We can calculate the result of parameter number being equal to 4. The answer to that is 3. Again, we need to calculate another recursive call, this time for number 3. Note that the result for number parameter being equal to 3 have been calculated before, but this result is lost along the way the recursive calls, since at each step we only know the results of two previous numbers. So we must carry out the redundant calculation like this. Now we can calculate the result of number being equal to 5, which is 5. Note that we had the answers for 4th and 5th Fibonacci numbers, which are needed to calculate the result at number 6. But we cannot apply the result of number 4 since it lost, so we need to carry out even more redundant calculations. And only now we can calculate the final result, which is equal to 8. Clearly, you can see that something is wrong with our calculations, although we've got the correct answer. It is obvious that we have carried out too much unnecessary calculations. In fact, the time complexity of this function is equal to 2 to the n. Space complexity is equal to On. You can see that this problem has necessary properties for dynamic programming being successfully applied. First, the final result can be calculated from the results of subproblems. Second, there are a lot of overlapping subproblems. Now let's look at a better solution to this problem. We will apply dynamic programming technique called memorization. It means we will add memo table to our solution where each intermediate solution of subproblems will be stored. Also, we add additional base case to our function. We have to check if we have the solution for a particular number, and if so, we will take the result from the table instead of calculating it again. Now let's perform the complexity analysis of improved solution. The first steps of this function is identical as in a naive function. We need to calculate the recursive functions until we reach the first base case. We have reached the base case, which gives answer 1. Remember, when we produce the answer, we also insert this answer into the memo table. The remaining steps are similar. Each time we produce the result, we add it to the table, and each time we call a function, we look at the table first. So far, the calculations have been as usual, but at this point we can use the first answer from the memo table. Let's go further. Now we get another result from the table. Finally, we get the last required result from the memo table. And we can calculate the final result, which is equal to 8. You can see that time and space complexity of memoized solution is equal to On. Let's look at another solution for Fibonacci numbers problem. This time we will use another dynamic programming technique called tabulation. This time our solution is not even recursive. We use local memo table for storing 3 Fibonacci numbers. Initially, it is the first 3 Fibonacci numbers. We iterate from third number up to nth number. We use our memo table as a cyclic array whose capacity is only 3 elements. The oldest Fibonacci number in the memo is constantly overwritten by the newest number. It is possible to store only the last 3 sequence numbers, because we need only 2 preceding numbers to calculate the current number. Keep in mind that it would not necessarily be the case for other type of problems. The final result is equal to the nth number in the memo, if the n is in the range from 0 to 2. If it is a greater number, we take a maximum value from the memo table. Let's analyze the time complexity of this function. The results of first 3 Fibonacci numbers, including 0, are stored in memo buffer. So we start from 3, we calculate third Fibonacci number and update our cyclic array. Then we do the same for the remaining numbers. The sixth Fibonacci number is equal to 8. This is the final result. The time complexity of this function is On. The space complexity is a constant since we do not use recursion, and we use the internal static buffer consisting of only 3 elements. Let's talk about advantages and disadvantages of tabulation and memorization. Tabulation has these properties. Code gets complicated when a lot of calculations are required. It is fast as previous state can be directly accessed from the table. Algorithm with tabulation usually outperforms a memoized algorithm by a constant factor if all subproblems must be solved at least once. All table entries are filled one by one starting from the first entry. Memorization has these properties. Code is easy and less complicated. It is slow due to a lot of recursive calls. If some subproblems need to be solved at all, memorized algorithm has the advantage of solving only those subproblems that are definitely required. The lookup table is filled on demand. All entries of lookup table are not necessarily filled. The key points of this lecture would be the following. Dynamic programming is an algorithm design technique where the problem is broken down into simpler subproblems and the final solution is calculated from the solutions of these subproblems. This technique helps to reduce a time complexity of subproblems. Dynamic programming can be successfully applied only for the problems that have optimal substructure and overlapping subproblems. The solutions of solved subproblems are stored and when needed can be reused for future calculations. Dynamic programming helps to reduce the space of subproblems in the way that overlapping subproblems are solved only once. Dynamic programming offers two approaches for space reduction of overlapping subproblems. Memorization, a top-down approach, and tabulation, a bottom-up approach. Thank you for your attention.